This talk deals with some neurophysiology topics that are usually hard to grasp by first and second year medical students. This is the fourth talk in a four-part series. The section outcomes are listed here. You do not need to read them. They will be covered during the course of this talk. This talk will be conducted in a question and answer format. The first question is, a motor unit is defined as a neuron, its axon, the axonal branches, and all the striated muscle fibers they innervate. A true, B false. The functional anatomy of striated muscle, based on Cherryton's model published in 1906, has a simple arrangement. An upper motor neuron in the cerebral cortex, labeled in this frame 1, makes contact with a lower motor neuron in the brainstem or spinal cord, labeled in this frame 2. The lower motor neuron makes contact with striated muscles. This arrangement allows us to understand a great deal of striated muscle physiology and pathophysiology. Striated muscles are present in the somatic effector system. The somatic effector system is present in cranial nerves and spinal nerves. Striated muscles are also present in branchial system. The branchial system is only present in cranial nerves. So now let's look at an striated muscle and its innervation. This drawing represents an striated muscle. Here we have cut it in half and turn one half towards us to see its inside constitution. The most important constituent of muscle is muscle fiber. Muscle fibers go from one end to the other end of the muscle most of the time. The structure I have just introduced corresponds to a lower motor neuron, or the second neuron in Cherryton model, as you can see in this frame. Now I am pointing to the axon and now to the contact between the axon and the muscle, as it was represented in the initial Cherryton model, but the reality is a bit different. The difference is that the axon goes inside the muscle, and there the axon breaks into multiple branches. These branches innervate many muscle fibers far apart from each other, as represented in this frame. So, by definition, the term motor unit is used for all muscle fibers innervated by one axon, the axon, and the neuron from which the axon originates. So the answer to this question is A. Next question. In an striated muscle, small muscle fibers contract before big muscle fibers because large motor neurons become activated by less current than small ones. A true, B false. When performing an EMG, once the needle is inserted in the muscle and the patient is asked to contract the muscle, initially softly and gradually using more strength, you will notice as the strength of the contraction increases that the amplitude of the spike changes. The amplitude of the spike reflects the size of the motor unit, and the size of the motor unit reflects the size of the motor neuron being used. So, initially, the spikes are small, corresponding to small motor units. These motor units correspond to small motor neurons, as we have just mentioned. As the contraction increases, taller spikes appear, These spikes correspond to bigger motor units and occur due to the recruitment of larger motor neurons. And when the contraction becomes even stronger, this is so because even bigger motor units are recorded due to recruitment of even bigger motor neurons. The contraction of a motor unit, large or small, is called motor unit action potential. Notice that the frequency of the motor unit action potentials increase in relation to the increase in force. This occurs in the small motor unit action potentials as well as in the medium size and large size motor unit potentials. Why smaller muscle fibers contract before larger muscle fibers? Because smaller motor neurons become activated before big motor neurons. Why smaller motor neurons are activated before larger motor neurons? In motor neurons, or for that matter in any neuron, excitation is directly proportional to the total membrane resistance. The higher the total membrane resistance of a neuron, the easier a neuron gets excited or activated, and inversely proportional to the total membrane capacitance. So the higher the capacitance, the harder it is for a neuron to be activated. The reason that the higher the neuron membrane resistance, the easier it is to excite a neuron can be easily deduced from Ohm's law. So a small neuron with its corresponding small surface area will have high total membrane resistance because of the small surface area, and for the same reason it will have a low total membrane capacitance. On the other hand, a large neuron will have low total membrane resistance because the surface area is large, and total capacitance will also be high for the same reason. Now we must again talk about Ohm's law to understand the effect of neuronal size and excitability. This law states that to generate a given electrical force in volts, that is a certain membrane potential, the higher the resistance, the less current that would be required to produce a similar change in membrane potential. Because current multiplied by resistance yield voltage. So in the small neuron, the higher the total membrane resistance makes little current produce a large voltage. In addition, the little total membrane capacitance of small neurons further contributes to the generation of high voltage with relatively small current because few charges are needed to charge the membrane. In a large neuron, the low total membrane resistance has the effect of increasing the amount of current needed to trigger an action potential. And since it also has more total membrane capacitance, it also requires more current to charge the membrane prior to excitation. So the answer to this question is B. Next question. Increasing the diameter of a neurite will produce an increase in effective electrotonic conduction by A. Increasing length constant, B. Decreasing length constant, C. Increasing time constant, D. Decreasing time constant. When we talk about neurites, we are referring to dendrites and axons. To answer this question, we will use the axon as an example. A thin axon will have a short length constant. Increasing the diameter of an axon will, as I have done here, increase length constant. How is length constant modified by increasing the diameter of a neurite? When dealing with length constant an increased axonal diameter, we need to consider two factors: membrane resistance and axial resistance, as expressed in this equation. The effect of increasing the diameter of a neuron in these two factors is better understood if, instead of representing a segment of an axon as a cylinder, we represent it as a rectangular prism. Representing the axonal segment as rectangular prism makes calculations easier. We will use a rectangular prism measuring 2 centimeters in length, 1 in width, and 1 in height, as represented here. Hence, with an area of 10 square centimeters and a volume of 2 cubic centimeters. We have done this to show the effect that increasing the size of a rectangular prism by a factor of 4 will have on membrane resistance, which is a function of the surface area, and axial resistance, which is a function of volume. As represented here, you can see that the area will increase to 160 square centimeters, that is by a factor of 16, whereas the volume will increase to 128 cubic centimeters, that is by a factor of 64. If we now consider membrane resistance and axial resistance, as represented here, we will find that the increase in size decreases membrane resistance by a factor of 16, corresponding to the increase in surface area, which would decrease length constant, hence slow down axonal conduction, but the increase in volume would have decreased axial resistance by a factor of 64. Thus, the net result of a 4 times increase in the size of an neurite is to increase the speed of conduction about 3 times. So the answer to this question is A. Next question. Myelinating an axon will produce an increase in effective electrotonic current by increasing length constant. A true, B false. The effect of myelinating an axon can be easily understood by considering the effect of myelin on length constant. Myelin increases membrane resistance and has no effect on axial resistance, thus greatly increasing length constant. Length constant is also referred to as space constant. So the answer to this question is true. Next question. Axonal conduction velocity is increased with a decrease in the dash of the axon. A. Diameter. B. Degree of myelination. C. Space constant. D. Capacitance. E. Membrane resistance. We already determined that myelination increases length constant and that increased length constant increases conduction velocity. Membrane capacitance is also decreased by myelination. A decrease in membrane capacitance is believed by some authors to further contribute to the expanding the distance traveled by the depolarizing current. So the answer to this question is D. Since this assertion is controversial, logical enough to ring true, the less charges spent charging the membrane under the myelin, the more charges available to flow inside the axon, but not fitting with the cable theory nor with the currently held assumption that electrotonic conduction is instantaneous. Answering this question is based on exclusion. Next question. How fast does a 20 micrometer 1A fiber conducts? A. 80 to 120 meters per second. B. 50 to 70 meters per second. C. 30 to 40 meters per second. D. 20 to 30 meters per second. The way of calculating conduction velocity of a myelinated fiber is by multiplying its diameter by 6 when the diameter of the fiber, which include axon and myelin cover, is more than 11 micrometers. The way of calculating the conduction velocity of a myelin fiber is to multiply its diameter by 4.5 when the diameter of the fiber, which include axon and myelin cover, is less than 11 micrometers. A way to determine the speed of conduction of a nerve is by taking the diameter of its thickest fiber, multiplying it by 6, and dividing the result by 2, as you can see in this frame. So the answer to this question is A. Next question. How fast does a 20 micrometer unmyelinated fiber axon conduct? A. 25 to 35 meters per second. B. 16 to 20 meters per second. C. 10 to 15 meters per second. D. 3 to 5 meters per second. In this frame, you can see the representation of one unmyelinated axon and one myelinated axon. Both have the same diameter, 20 micrometers. Unmyelinated axon conduction velocity can be calculated by finding the square root of the diameter of the axon. Using this factor, the calculated conduction velocity of a 20 micrometer unmyelinated axon is 4.5 meters per second. A myelinated axon of the same size will conduct at 120 meters per second. As you recall from the previous question, the conduction of myelinated axon increases exponentially by a factor of 6 for each micrometer. In this new frame, I have represented a 500 micrometer unmyelinated axon and a 500 micrometer myelinated axon. Myelinated axon of 500 micrometers do not exist, but I am using it for comparison. The unmyelinated axon calculated conduction will be 22.3 meters per second. The conduction of a myelinated fiber with an equal diameter will be 3000 meters per second. Here, as you can see, we have schematically increased the axon to 1000 micrometers or 1 millimeter. The calculated conduction velocity for the unmyelinated axon is 32 meters per second. The calculated velocity of a myelin axon of that size would be 6000 meters per second. Again, myelinated axon of this size do not exist. The thickest unmyelinated axons are found in the squid. The diameter varies from 0.5 to 1.5 millimeters. Thus, the calculated conduction velocity for a squid axon of 1 millimeter would be 32 meters per second. The experimentally measured speed of conduction of a 1 millimeter axon is 25 meters per second. The thickest myelinated fiber in human is 20 micrometers. The conduction velocity of such fiber is 120 meters per second. Hence, the answer to this question is D. Next question. Stimulators under regular conditions produce depolarization under the dash. A. Anode, B. Cathode, C. Anode and cathode, D. None of the above. I will address this question by telling you about 3 mind experiments. Here goes the first one. This figure shows an stimulator. The stimulator is in the off position. You can see the anode and the cathode. The skin and axon are also labeled. On the right side of the screen, I have placed a recording device. Now the stimulator has been turned on and an action potential arises under the cathode. The electrotonic current produced by the action potential spreads in both directions, the current advancing towards the recording device goes on to produce a wave. Now let's do experiment number 2. Again, we start with the stimulator off, but now we use a plier to crush the area of the axon below the anode. Then we turn the stimulator on, and again an action potential will occur under the cathode, generating a current in both directions. The current will stop in the crush area, but the recording device will record a wave when the current reaches it. Now we will conduct the third experiment. Again, we start with the stimulator off, but instead of crushing the area under the anode as we did last time, this time we place the pliers in the area below the cathode and crush that region. Now we turn the stimulator on as we have done in this frame, but no action potential is generated. So the answer to this question is B. Next question. Which axons are easier to excite with electrical stimulation? A. 1 micrometer myelinated axon, B. 6 micrometer unmyelinated axon, C. 9.5 micrometer unmyelinated axon, D. 8 micrometer myelinated axon. Excitation is greatly influenced by two factors. The first factor is the intensity of the electrical stimulation. The intensity of an electrical stimulation corresponds to the current density produced by a stimulator. The current density is directly proportional to the magnitude of the stimulation, which is given in milliamps, and the duration of the stimulation, which is given in milliseconds, and inversely proportional to the area involved by the stimulus. The area is given in square millimeters. The second factor relates to axonal size and presence or absence of myelin. In unmyelinated axons, excitability is directly related to the diameter. Axons with larger diameters excite with less intensity of stimulation than those with smaller diameters. The same principle holds for myelinated fibers. Thicker myelinated axons are easier to excite than thinly myelinated axons. Yet, when comparing myelinated and non-myelinated axons, the same size myelinated axons excite easier than unmyelinated axons. Why myelinated axons are easier to excite than unmyelinated axons of the same size? The reason myelinated axons are easier to excite than unmyelinated axons is that in myelinated axons, electrical current concentrates in the nodal ranviers. Hence, if we go back to the current density formula, we can see that myelination, by being relatively resistant to current, restricts the area of the axon exposed to the current, thus decreases the area exposed to the current, thus increasing current density. So the answer to this question is D. Next question. Myelinated axons are more easily excitable by increasing the magnitude of the current than similar size axons with no myelin. A true, B false. There are many factors that influence nerve excitability, as we just previously mentioned. Among them are axonal size, that is axonal diameter, and myelination. The red thunder I have just added to this frame implies a stimulus intensity in milliamps. The smaller thunder indicates a weaker stimulus, the larger one and a stronger stimulus. The duration of both stimulus is 0.2 milliseconds. The strong stimulus is strong enough to produce excitation in all fibers. The smaller stimulus produces excitation in the thicker unmyelinated axon, but does not excite the thinner unmyelinated axon. On the other side, we have myelinated axons and unmyelinated axons of equal size. The small stimulus excites the myelinated axon, but does not excite the unmyelinated axon of the same diameter. So the answer to this question is true. Thank you very much for your attention.